It's time to start our second podcast for the Kinetics unit in Chapter 14 of AP Chemistry. We ended our last video talking about the first order processes and how if you graph natural log of the change in concentration versus time, you get a straight line with a first order process. Tonight we're going to talk about a second order process. This is one in which rate depends on the concentration to the second power. So as the rate doubles, as the concentration doubles, the rate quadruples. So it's squared, second power. Or if you have two different reactants, each one is first order reaction raised to the first power. For a second order reaction with just one reactant, you get this relationship. Instead of a natural log of the concentration as in first order, you get an inverse of the concentration as for your concentration at time t, and that will equal your slope reaction constant, rate constant times time, plus 1 over the original concentration. This is in a y equals mx plus b form as well. If you plot this, you will get a straight line with a slope k and intercept 1 over the original concentration. So here's some data of nitrogen dioxide gas breaking down into nitrogen monoxide plus 1/2 mole of oxygen. Here's the time, here's the concentration. When you graph this data as a natural log looking for a first order, you see that it is not a straight line. So it can't be a first order. However, when you graph 1 over the concentration versus time, you get a straight line. Now notice in this case, it's a positive slope to the graph. So as we saw in our equation, it's a positive line to the slope. So you can see that 1 over the concentration time t equals the rate constant, which is the slope, rise over run. It's a positive value times the time plus 1 over the original concentration, which is the y-intercept. So depending on which process gives you a straight line, you can determine the order in this way, as well as knowing the rate and the concentration change process that we looked at earlier. Okay, half-life is another useful piece of information about any kinetic process. Half-life is the time required for the reactant to decrease in concentration by half of its original value, as we did in our M&M lab. So in this particular case, you've got CH3NC at a certain pressure, and it breaks down by half, the pressure reduces by half in a certain amount of time. It looks to be about 12,000 seconds. And if you go from here to another half, that's another approximately 12,000 seconds. It's a consistent half-life to cut the concentration in half. Now, one way to simplify our first and second order reactions to think about half-life is to compare the original concentration, take that times 0.5, and that will equal your final concentration. So in that way, you can do some substitutions and make some generalizations about half-life. Mathematically, the half-life of a first order process is 0.5 of the original concentration over the original concentration. Take the natural log of that equals negative k times t half. You get this generalized half-life equation for a first order because when you substitute your natural log A of t for the natural log of 0.5 times your original concentration into your equation for first order reaction kinetics. You can substitute natural log of A0 in for AT and subtract natural log A0 from both sides. Now when you subtract natural logs, one way to simplify that is just take the natural log of the divisor. So 0.5 AO divided by A at time 0. And that will equal negative KT. Now we can simplify that even further, as you can see, by canceling the original concentrations, rearranging and solving for negative 0.693 as the natural log of 1/2, moving the negative sign and the rate constant, and you get a half-life of 0.693 over K. Interesting to note here is the fact that half-life of a first-order reaction does not depend on concentration. Half-life is independent of the concentration because you get half each time when you do a first-order reaction. That's pretty cool. So no matter what half-life decomposition you get, it's 0.693 over the rate constant. For a second-order process, do a similar substitution for the original concentration. For the concentration at time t, substitute 0.5 times the original. Rearrange so that if you take 1 divided by 0.5, you get 2. And that's going to equal K times T 1/2 plus 1 over the original. Then you can subtract 1 over the original concentration. So you're subtracting 1 over the original from both sides. That leaves you with 1 over the original concentration equals the rate constant times T 1/2. In this case, it does depend on the original concentration when it's a second order process. Okay. That's enough for tonight's podcast, but I want you to try some of these problems with second order and half-life calculations. So in your textbook, I'd like you to go to page, I'll write this down for you, to page 592 and 593 in the text and look over sample exercise 14.9 for an example, and the work and the answers are all there for that half-life problem. But then I want you to try practice exercise numbers 1 and 2 on page 593. Those are sample exercises 1 and 2 on page 593. Please put those answers in your summary form, and we'll go over those in our next class if you need help with those. Have a good night. Take care. Bye.